What I'd like to do now is I'd like to talk about graphs that are flipped over the center line, and I'd also like to talk about graphing secant and cosecant. I will give you an example of graphing cosecant. To do that, we use a guide function. The guide function that we use is sine of theta. You also, if you're wanting to graph secant, you would have to use a guide function of cosine. We talked about this when we talked about basic shapes of trig functions. Now, we haven't seen any kind of flips over our center line. And so what I want to do is I want to talk about just a simple example, y is equal to negative sine of theta, and see what that negative value does. Okay, now sine of theta, we know that here we're not having any kind of change to the amplitude, so we'd have up at 1 and down at negative 1 being the values determined by our amplitudes. Generally, sine starts at 0, 0. Okay, that will stay the same. The difference as far as having the negative in the front means you go the opposite direction from what you normally would in this case. In other words, you would normally go up to positive 1 above the pi over 2. In this case, you would go down to negative 1, and then back to 0, and then back to positive 1, and then back down to 0. And so this would be your basic shape for graph of negative sine of theta. Okay, let me do this for negative cosine. Okay, if you're looking at graphing y equals negative cosine of theta, then what you will generally have is you will have your amplitudes at 1 and at negative 1. You'll have the same quarter points that you normally do. There's been no change to the quarter points. Make sure that anytime you're graphing for me, you always label your quarter points. Okay, the difference here is that my normal graph of cosine starts at positive 1. Because this is negative cosine, I would start at negative 1. But then I would go to 0, and then to positive 1, to 0, and then back down to negative 1. And so essentially what has happened is my graph has been flipped over that center line. Okay, let's look at an example of a graph for cosecant. All right, let's say that I'd like to graph over one period f of theta equals negative 1/2 cosecant, and then on the inside I have 3 theta minus pi over 2, and then that's it. All right, the two things that I need to notice here is I need to notice that first of all I'm graphing cosecant. To graph cosecant, I'm going to use as a guide function actually this particular expression. Let me call this g for guide. So as my guide function, I'll use g of theta equals negative 1/2, not cosecant, but its reciprocal, sine of 3 theta minus pi over 2. Okay, once I graph the guide function, I know that cosecant goes basically the opposite direction, and it has asymptotes. And so once I graph the guide function, it will be easy to graph cosecant from that. The only danger in this is make sure you remember that you're graphing the guide function and that the function you actually want to graph eventually is the cosecant. Don't leave it just a sine. Okay, now for the guide function, a couple of things to note. Number one, we have an understood amplitude of 1/2. It's negative, which indicates that we're going to have a flip over the center line. All right, now don't ever put a negative sign with an amplitude. Amplitude is basically the distance from the center line up or the center line down. The negative here with it basically just says that whatever the center line is, I'm going to be flipped over that center line. Now the center line, we don't have a value over here at the end, so we'll say it's plus 0, so we know that the center line is just 0. Okay, that's what it normally is when I graph my basic trig functions. All right, from here, I see that we have a change to my quarter points. All right, so I need to go in and I need to determine what my first and last quarter points are, my periods, my increments, and all of that. All right, right? Normally, for sine, I would have my angles lying in between 0 and 2 pi. However, I have a change to my angle in this particular situation. So I need to set 3 theta minus pi over 2 in between 0 and 2 pi to solve. Right? I need to add over. Actually, in this case, I am going to do the same thing I did on a previous example. I'm going to multiply everything by the LCD, which is 2. That will clear my fractions. So I'll multiply this by 2, 3 theta by 2, pi over 2 by 2, and the 2 pi by 2. That will result in 0 on the left, 6 theta minus pi, and then 4 pi on the right. Okay. Add pi to all sides. So on the left, I end up with pi right here. And then on the right, I end up with 5 pi. Divide by 6. And my first quarter point would be pi over 6. And my last quarter point would be 5 pi over 6. So I'll go ahead and label those here so that I remember quarter point 1, quarter point 5. From here, the next thing to do is to determine the period. The period I find by subtracting the largest quarter point minus the smallest quarter point. So that's 5 pi over 6 minus pi over 6, which ends up being 4 pi over 6. That reduces down to 2 pi over 3. My period normally for sine is 2 pi. You see that this period has been shortened. Okay, from here, what I need to do is I need to figure out my increments. My increments are determined by taking 1/4 of my period. So 1/4 of 2 pi over 3. Okay, I can reduce this. So I'll have pi over 6 as my increments. From here, I need to determine my quarter points. Quarter point number 1 should be the leftmost value in the interval here, pi over 6. To determine my next quarter point, I would add pi over 6 plus my increment. My increments also happen to be pi over 6. So pi over 6 plus pi over 6 is 2 pi over 6, which reduces down to pi over 3. Now, because my increments are in pi over 6's, my quarter point 2 is technically pi over 3 when you reduce it, but it may be helpful to use this in the next step because it already has that common denominator. So that's what I will do there. So quarter point number 3, I will use 2 pi over 6, and I will add my increment pi over 6. I'm sorry, that's supposed to be 2 pi over 6. So this becomes 3 pi over 6, which reduces down to pi over 2. Okay, I'll do the same thing. I'll kind of cheat, and I'll use this in the next step. Quarter point number 4, I have 3 pi over 6 plus pi over 6, which is 4 pi over 6. That reduces down to 2 pi over 3. Quarter point number 5, I already know that that should be the last number from my interval up above. It should be 5 pi over 6. I'll cheat, use that. 4 pi over 6 plus pi over 6 is 5 pi over 6. So I know I've done all my work correctly when I get to that last quarter point of 5 pi over 6, and it matches up with what I have up above. Okay, it's now time to graph my function. In graphing this function, I'm going to keep in mind 2 things. Okay, number 1, I'm first going to graph my guide function. Okay, let's go ahead and put the quarter points on here before I start. My quarter points, we had pi over 6 was the first one. The second one was pi over 3. The next one was pi over 2. The next one was 2 pi over 3. And then the last one was 5 pi over 6. All right, my quote amplitude for this particular problem was 1/2. So I'll go a half a unit above and a half a unit below my center line, when my center line here was 0. Okay, from here I want to graph my guide function. My guide function was negative 1/2 sine of 3 theta minus pi over 2. Because it's negative, that means it was flipped over the center line. Normally, I would start here and go up. Because it's flipped, I start here and go down. So here are the points for my guide function. Now, because this is a guide and not actually the function that I'm wanting to graph, I will use a dotted line. Okay, so that's my guide function. Wherever my guide function crosses the center line, I will have asymptotes. Let's say that in this case, my center line had been actually negative 12, then wherever this function crossed negative 12, I would have asymptotes. So vertical asymptote here, here, and there. Once you have the asymptotes in your guide function, you can then go and you can actually graph the cosecant function. Okay, the graph in black is the cosecant function. All right, this concludes the example of graphing trig functions.